Antimatter. It sounds like something out of science fiction, but it's real, it exists, and a tiny amount of it could theoretically power a city. So what exactly is this mysterious substance, and why is it both one of the most promising and most dangerous materials in the universe? Let's start with the basics. Every particle of ordinary matter has an antimatter twin. An electron, which carries a negative charge, has a counterpart called a positron, which is identical in every way except it carries a positive charge. Protons have antiprotons. Neutrons have antineutrons. When a particle meets its antimatter twin, they don't just collide, they annihilate each other completely, converting their entire mass into pure energy. This is the most efficient energy-producing reaction known in physics, far more powerful than nuclear fission or fusion. The idea of antimatter wasn't dreamed up by chance. In 1928, a physicist named Paul Dirac was trying to combine quantum mechanics with Einstein's theory of relativity. His equations kept producing a strange result. They predicted the existence of a particle just like the electron, but with opposite charge. Dirac initially doubted his own math, but just 4 years later, in 1932, physicist Carl Anderson detected this exact particle while studying cosmic rays. He named it the positron, and Dirac's prediction was confirmed. Antimatter had gone from mathematical oddity to observed reality. So if antimatter exists, why don't we see it lying around? This is one of the biggest mysteries in physics. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter, which means they should have annihilated each other completely, leaving nothing behind. Yet here we are, made of matter, in a universe full of matter. Somehow, a slight imbalance tipped the scales in favor of matter, and scientists still don't fully understand why. Since antimatter doesn't naturally stick around on Earth, we have to make it ourselves. Facilities like CERN in Switzerland use massive particle accelerators to smash protons together at incredibly high speeds. These collisions sometimes produce antiprotons, which scientists then capture using powerful magnetic fields, since antimatter would instantly destroy itself if it touched the walls of a normal container. And this is where things get expensive. Producing antimatter is, quite simply, the most costly process humans have ever undertaken. Estimates suggest that manufacturing just 1 gram of antimatter could cost anywhere from tens of billions to over $100 billion. To date, humans have created only a tiny fraction of a gram in total, and storing it is just as difficult as making it, since any contact with normal matter causes immediate annihilation. So why bother? Because the potential uses are extraordinary. In medicine, antimatter is already at work. PET scans, used every day in hospitals, rely on positrons to create detailed images of the human body, helping doctors detect cancer and other diseases. Looking further ahead, scientists have proposed antimatter as fuel for deep space travel. A spacecraft powered by matter-antimatter annihilation could theoretically reach speeds and efficiencies far beyond anything chemical rockets can achieve, potentially cutting travel time to distant planets dramatically. But with great power comes serious danger. Because antimatter annihilation converts mass directly into energy, even a small amount could release a devastating amount of destructive force. Just 1 gram of antimatter meeting 1 gram of matter would unleash an explosion comparable to a large atomic bomb. This has fueled fears and plenty of science fiction about antimatter being weaponized. The reality, thankfully, is reassuring. The amount of antimatter we can currently produce is so minuscule and so expensive that creating enough for a weapon is far beyond our current technology and likely will be for a very long time. So where does that leave us? Antimatter remains one of nature's most fascinating substances, a mirror image of everything we're made of, capable of producing energy on a scale we can barely imagine. It has already improved medicine. It may one day power our journeys to the stars, and it continues to challenge our understanding of why the universe exists the way it does. The story of antimatter is still being written, and the next chapter might just come from a laboratory pushing the boundaries of what's possible.